I wanted to make today's video shorter than day one. That was too long. So today I have basically one goal. I'm going to show you how we can derive the equations for constant acceleration of an object using calculus. If you're rusty with calculus or you haven't gotten to integration yet, that's okay, don't worry. We're not normally going to have to do this in class, but I think that this is the best way to show where those expressions come from. Your main goal in the class will be to use these equations that I arrive at. So we are going to start with the idea that our acceleration is constant. So since it's constant, I'm just going to use the letter A to denote whatever value that acceleration might have. If you remember, we saw that the definition of acceleration, we could express it two ways in terms of derivatives. Because it's the change in the velocity over time, we can call it the derivative of velocity with respect to time. And I do want to mention that in this case, I'm speaking of instantaneous acceleration, just to be clear. Although if the acceleration is constant, the average value and the instantaneous value would be the same. So, going back to the definition, it's the derivative of velocity with respect to time. Because of the fact that velocity can be expressed as the derivative of position with respect to time, we can also call it the second derivative of position with respect to time. That's just some simple review. In any case, we're going to start with this expression, this definition, that the acceleration is the derivative of velocity with respect to time. Again, remember A here is a constant value. That means it could be a number. It could be 3, it could be -5, it could be any number, but we're just trying to be very general. What I'm going to do is I'm going to multiply both sides by dt. And when I see these are called differentials. This really says to me I would want to integrate it. So we would do the integration sign. On the left-hand side, we're going to integrate over time. On the right-hand side, we're going to integrate over velocity. Now, what I'm going to do is I'm going to make these definite integrals, which means I have limits. I'm going to start at time equals 0 and go to some time. I'm going to be not so specific about that. Now, the limits on velocity have to correspond to the limits of the time. So the velocity that I use for the lower limit has to be the velocity that it had at time equals 0. We call that v sub 0, or v naught, which stands for initial velocity. And then the velocity at the arbitrary time t, which is our upper limit, would just be some arbitrary velocity v. Now, on the right-hand side, I can take the acceleration term outside of the integral because of the fact that it's a constant. Now I'm going to go up here just to save some room. When I integrate on the left-hand side, when I integrate dt, I get time, and it's going to go from 0 to t. Those are my limits. When I integrate dv, I just get v, which is going to go from v naught to v. When you evaluate at that limits, remember I'm going to get a times t minus a times 0. That's evaluating at these two limits. And I'm going to get v minus v naught. So this is just 0. So I'm left with at equals v minus v naught. And so if I rearrange this, I get v equals v naught plus at. This is my first equation that I'm going to use. This tells me if I know my acceleration and I know my initial velocity, All I have to do is plug in a value for time, and that would give me the velocity at that time. This is our first equation. I'm going to start with this one now, and then to get my next one. And I'm going to use the definition of what velocity is. It's the derivative of position with respect to time. Again, I'm going to multiply both sides by dt, because that'll give me differentials on each side that are different. On the left-hand side, notice the only variable I have is t, and that goes with my differential of dt. So all my time, or t's, are on the left-hand side. On the right-hand side, I just have dx. Then I'm going to integrate. My limits for time are the same as they were the last time, going from 0 to t. On the right-hand side, again, my limits have to correspond to the limits I put on time. So the lower position limit has to be the position when time was 0. We call that x naught, which is the initial position, and then the upper limit is just going to be x, representing the position at this time t. When I integrate, all right, so the first two equations are the equations that we derived on the previous slides, and these are going to be very important equations that we use for constant acceleration motion. We'll be studying constant acceleration motion that's in the horizontal direction, as well as free fall, which is vertical constant acceleration with the acceleration due to gravity. If we took these two equations and eliminated time, we would get the third equation shown here, which is actually quite handy sometimes because of the fact that sometimes we don't have the knowledge of time, but we have the other quantities that allow us to find what we're looking for. These are the very basic equations we'll be using. It's important that you know these. The way that we use them in a problem is we put the specific values that we're given for the initial velocity, position, and acceleration, and then use other things that we might know in order to find what we're asked to find. For instance, if we want to find position at a specific time, if we know initial position, velocity, and acceleration, we just need to put in the appropriate time value, and we will get where the object was at that time. I know that maybe you might be rusty with your calculus, or maybe you're not clear on how to do integration yet, but don't worry about that. If you are rusty, at this point we're not expecting you to do the integration to use these equations. You just use them and make them fit your specific problem. I was just trying to show you where that information comes from. So that's it for today. As promised, this is going to be a much shorter video than the previous one.